Welcome to lecture 7 on properties of triangles. So, in this lecture we will be discussing and solving some problems related to whatever we have learned in the last 6 lectures. So, here is the first problem. It states that if D, E and F are the distances between the orthocenter and the vertices A, B, C of a triangle ABC, then we have to show this particular equality. So, let us draw the triangle ABC and let us try to show these distances in the next slide. So, let us suppose that this is our triangle ABC. Let us draw the orthocenter first. So, we firstly have a perpendicular from the vertex A to the opposite side BC, and then this is the other perpendicular from vertex B to the opposite side AC, and these two perpendiculars intersect at the orthocenter. And then we had also shown in one of the previous lectures that the third perpendicular from the vertex C to the opposite side AB will also cross through this point O. Therefore, this angle is also 90 degrees. So, D, E and F are the distances between the orthocenter and the vertices. So, let us say that this distance is D. So, D is basically AO and the distance OB is E and the distance OC is F. Of course, these lengths are, this is A, this is B, this is C. So, the equality that we are asked to show is that A by D plus B by E plus C by F equals ABC over DEF. So, if we take DEF to the other side, this equality is the same as AEF plus BDF plus CDE equals ABC. So, what we see is that on the left hand side we have a sum of 3 terms, where each term is basically the product of 2 of these distances. So, 2 of the distances between the orthocenter and 2 of the vertices. So, for example, the first term here is the product of EF with A. So, A is this. So, one way to get this product is, let us try to concentrate on this triangle BOC. So, the area of this triangle BOC is what I am shading with green. So, this area, we hope that this area will depend on the product of E and F, and the reason is because this angle over here is 90 degrees. So, the area of this triangle BOC will be, if we treat this as base. So, therefore, the area of triangle BOC is half times base. So, let us take this OB as the base of the triangle BOC. So, half times base times height. So, the height is going to be this distance between the foot of the perpendicular from B, which is this point and this point. So, this particular length is going to be the height, but to know this length in terms, we would like to express this length in terms of F, because that is how we can get the product of E and F. So, for that we need to focus on this right angle triangle here. So, let us say I mark this point as E. So, I am right now considering the right angle triangle OCE. So, this will be E times CE. So, now we need to first find out this angle, because if we know this angle, then clearly CE is equal to f times the sine of this angle. But this angle is not very difficult to find out, but since we are interested in finding out this angle, it will be easy to find out this angle if we knew this angle, and this angle is not very tough to find, because if we see this right angle triangle over here, if you see this right angle triangle, then this is angle A, and therefore, this particular angle is pi by 2 minus A. And then we see this triangle, right angle triangle OEC. Since this is pi by 2 minus A, it is now clear that this angle has to be A. And therefore, this if we again look at this right angle triangle, then this length will simply be f times sine A, and therefore, the area of this particular triangle here will be half times base times the height of this triangle, which is f sine A. But what we have here is also the product of EF with the length of the side opposite to the vertex A, which is A, and that is not very tough to write down, because we can actually multiply and divide this expression with. So, when we multiply and divide this expression with A, what we end up getting is AEF times sine A over 2A. Now, from the discussions in the previous lecture, we already know that in any triangle ABC, the ratios A over sine A, B over sine B, and C over sine C, these ratios are equal, and they are in fact equal to twice the radius of the circumcircle of this triangle ABC. So, R is the radius of the circumcircle of this triangle ABC. So, from here we see that sine A over 2A. So, if we just see this equality here, then it follows that sine A over 2A, this is equal to 1 by 4R, and if we substitute this with 1 by 4R, what we get is AEF over 4R. This is a very important step in solving this problem, because since the left hand side here has only AEF, whereas this particular term has another A here and the angle A in the numerator, right. So, we would like to therefore replace this with something which will appear in the other two similar terms also, and we know that the circumcircle of any triangle ABC as well as the circum radius is unique. So, this is an expression. So, this is the expression for the area of triangle BOC. Similarly, in the previous figure, using similar steps, one can show that the area The next triangle we can consider is the triangle AOC, which I am shading in red. Using a similar step used to derive the area of triangle BOC, it can be shown that area of triangle AOC equals BDF over 4R. So, this is basically the second term over here, and then we have this other triangle here, which is AOB. So, I am shading the triangle AOB in black. Again, it is not very difficult to show that the area of triangle AOB is equal to DE into C upon 4R. So, this DEC is basically this third term, and one can now clearly see that if we add up these three areas, then we get the entire area of the triangle ABC, and that is what is happening here. We are adding these three terms. So, if we add these three areas, what we get is that area of triangle ABC is equal to area of triangle BOC plus area of triangle AOC plus area of triangle AOB, and using the expressions of these areas from the previous slide, we have the final expression for the area of triangle ABC to be equal to AEF upon 4R plus BDF upon 4R plus DEC upon 4R. But we have already shown in one of the previous lectures that the area of a triangle, any triangle ABC, is always equal to. So, we have shown that this is always equal to the product of the lengths of the three sides divided by 4 times the circumradius of the triangle. So, this is a known result which we have already shown and proved in one of the previous lecture. It has been shown, and we proved it rigorously. So, then basically what happens is that this and this has to be equal. So, therefore, we have shown that this and this and this are equal, and since 4R is common to the denominator everywhere, we ultimately have shown that ABC is equal to AEF plus BDF plus DEC, and this is precisely what we were asked to prove in the question. So, this finishes the proof of the first question, or the solution to the first question. Let us take another interesting problem. So, it is said that let P1, P2 and P3 be the lengths of the perpendiculars from the vertices of a triangle to the opposite side, and then it is asked to show that this product of the lengths of these three perpendiculars is equal to the product of the squared lengths of the sides of the triangle upon 8 times the cube of the circumradius. So, let us again draw a triangle ABC. So, now we also draw the perpendiculars from a vertex to the opposite side. So, these are the 3 perpendiculars. So, let this length be P1, let this be P2, and let the third one be P3. Of course, this we represent this length by A, the length of this side by B, and the length of this side by C. Now, the area of this particular triangle ABC equals half into base. So, let us take this as the base, the side BC as the base. So, half into A times the height is going to be this length P1. So, I will denote the area by delta. Which in turn is equal to, so this entire area, instead of taking this as the base, I can take this side AC also as the base. So, if this is the base, then the area is half into base, which is B, into height, which will be P2, and that of course has to be equal to this, because they are both area of this triangle ABC. And similarly, if we take this side AB as the base, then the area will be half into base, which is C, into height, which is P3. This length is P3. So, these 3 are all equal, and they are equal to the area of the triangle ABC. From this first equation we get P1 equal to 2 delta by A. From the second equation we get P2 equal to 2 delta by B. From the third we get, from the third equation we get P3 equal to 2 delta by C. The reason I expressed P1, P2 and P3 in terms of delta and A is because we need to calculate the product of P1, P2, P3 on the left hand side. So, if we take the product now, we get P1, P2, P3 equal to, so we multiply all these expressions on the right hand side. So, it is equal to 2 delta by A times 2 delta by B times 2 delta by C, which is equal to 8 delta cube upon A, B, C. And here we will again make use of the formula that we just saw on the previous slide, which is that the area of any triangle is equal to the product of its 3 sides divided by 4 times the circumradius. So, if we replace this expression instead of using delta, if I use this over here, we end up getting P1, P2, P3 to be equal to 8 times ABC by 4R cube upon ABC, which upon simplification gives us A square B square C square upon 8R cube. And this is exactly what we were asked to show in the question. So, this also finishes the solution to the, this finishes the solution to the second problem. Let us consider the third problem, where we are asked to show that in any triangle ABC, the centroid lies on the straight line segment joining the circumcenter to the orthocenter, and further that it divides this line segment in the ratio 1:2. So, let us draw a triangle ABC. So, let this be our, so this is our triangle ABC over here. And for the circumcenter, we first draw the perpendicular bisectors of the three sides. So, let us say this is the perpendicular bisector of the side BC, and let us say that so this is the perpendicular bisector. So, this angle is 90 degrees of the side AB. Let us say both of them meet here. The third perpendicular bisector will also pass through this point, which I will denote with the letter P. So, P represents the circumcenter of this triangle ABC. For the orthocenter, we drop perpendiculars from each vertex to the opposite side. So, let this be one of the perpendiculars from A to BC, then let this be the perpendicular from B to the opposite side AC. Then this point where these two perpendiculars, and in fact the third perpendicular from C to the opposite side AB is also going to pass through this point over here. So, this point, which is the point of intersection, or the common point of intersection of all these three perpendiculars, is called the orthocenter of the triangle ABC, which I denote with O. I then consider the straight line segment joining O and P, which I have drawn in green. So, we are asked to firstly show that the centroid, let me denote it by G. So, the centroid G of triangle ABC lies on the line segment OP, and further that OG divided by GP is equal to 2. So, this is what we are asked to show in this question. So, towards proving this question, what we will do is that we will, let us say that we denote this point here by D and this point here by E, and then let us join the vertex A with this point D over here with a straight line. So, we join A and D with a straight line, and obviously this straight line which I have drawn in black is going to intersect the line segment OP at some point over here. So, let me denote this point of intersection with the alphabet. So, we will denote it with the point F. So, this is point F over here for us. And now, let us focus all our attention on two triangles. The first triangle is OAF OAF, which is this particular triangle, and the other triangle is PDF, which is this little triangle PDF. So, we are considering two triangles, triangle OAF and triangle PDF. Now, since both this blue line or blue line here and this red line here, both of these lines are perpendicular to this line BC, it is clear that AE is parallel to PD. So, these two are parallel because both of them are perpendiculars on this side BC of the triangle ABC. though in the figure it might not exactly be appearing as parallel, but they are parallel. And because they are parallel, it is very much clear that all the three angles of this triangle are equal to the corresponding three angles of this triangle PDF. So, therefore, OAF and PDF are going to be similar triangles, and that is not very difficult because this particular angle here will be equal to this angle. So, angle PDF will be equal to angle OAF, and angle AOF will be equal to angle FPD, and of course, this is a vertical, these two are vertically opposite angles. So, therefore, they are equal. Now, because these two triangles are similar, one can very easily say that AO, so AO divided by PD equals OF divided by FP. This follows from the similarity of these two triangles very easily, and also this is further equal to AF divided by FD. Another point to be noted is that since this particular blue line is the perpendicular bisector of this side BC, it is clear that this point D is actually the midpoint of this side BC, and therefore, when I join this vertex A with D, this line segment AD happens to be a median of the triangle ABC. So, this line AD is actually a median. So, this is actually a median, and that is because D is the midpoint of BC. So, let us keep that in mind. So, AD is a median. So, our next goal is going to be able to derive some kind of an expression for this ratio, or let us say for these lengths AO and PD. From our previous lectures, we already know that if we have any triangle, let us take a triangle ABC over here, and let us draw the perpendicular. So, these are the three perpendicular bisectors which are meeting at this common point P, and P is the P is the circumcenter, because with P as a center and radius equal to PB, if we draw a circle, then that circle is basically going to touch all the three vertices A, B and C. So, this is the circumcircle of the triangle ABC. So, these three are the perpendicular bisectors, and this basically is the point D in our problem that we have right now, question number 3, and we are interested in finding this length PD. Now, if I join this P with B, so let me join this P. So, P is the circumcenter and I am joining it with B and C. So, from basic high school algebra, we know that if this, obviously this angle is A, and therefore, this entire angle will be equal to 2 times A. That is because if we look at this particular circle, then this is the circumcircle whose radius whose center is at P. So, from basic high school algebra, we know that this particular angle will be twice of angle A. And then further, because this is 90 degrees and this point D is the midpoint of BC, it is not very tough to show that this particular angle here, this angle is in fact A, because this perpendicular bisector is also going to bisect this angle, and that is not very easy, not very difficult to show. One can show it by using by showing the congruency between this triangle and this triangle. And of course, this particular distance between the vertex B and the circumcenter P is the circum radius, which we denote with R. So, this is the circum radius of the triangle ABC, and then we just have to look at this right angle triangle PDB. PDB. So, in this right angle triangle, this is R, this is A, and therefore, it is clear that this length PD is simply equal to R cos A. So, from this from here we see that PD is equal to R cos A. Next, we will see the distance between the vertex A and the orthocenter O, and that we have already seen in one of our previous lectures that this distance AO is in fact equal to 2R times cos of A. So, this we have already seen in one of the previous lectures. So, if we substitute this AO with 2R cos A and PD with R cos A, then what we end up getting is that these ratios are equal to 2, and therefore, what we see is that AF, which is this distance, is twice of FD. We have already seen that AD is a median of the triangle ABC, and this point F, which lies on AD, divides the median in the ratio 2:1, and therefore, it must be the centroid, and therefore, it must be the centroid, because centroid is the unique point which divides all the three medians in the ratio 2:1, and therefore, this point F is nothing but the centroid G of the triangle ABC. And further, it is very clear that this point F is also on the straight line, the green line OP, which joins the orthocenter O with the circumcenter P, and therefore, this finishes the proof of the first part of the question, since clearly F lies on this green line segment, and therefore, and since F is nothing but the centroid of the triangle ABC, it is clear that the centroid does lie on the straight line segment joining the orthocenter and the circumcenter. And further, from this ratio itself, what we see is that OF divided by FD is 2. So, this is OF and this is FP. So, OF divided by FP is equal to 2, and that basically proves the second part of the question, that the centroid divides the line segment joining the orthocenter and the circumcenter in the ratio 2:1. So, that finishes the solution to the third question. Let us take another very interesting problem. This is one of the JEE problems of previous years. So, in this problem, it is said that we have a triangle where the sides are 3 consecutive natural numbers, and that the largest angle happens to be twice the smallest one, and the problem is asking us to find the lengths of the sides of this triangle, which satisfies these two properties. So, let us say that this is our triangle ABC, and let us say that the smallest angle is this angle, which I will denote with let us say alpha, and let us say that this is the largest angle, and in the problem it is said that the largest angle is twice the smallest one, and since the smallest one is alpha, the largest one has to be 2 alpha. Let the sides, the 3 sides are natural numbers and they are consecutive natural numbers. So, let the 3 sides be x, let them be x minus 1, x and x plus 1. So, these are the 3 sides of this triangle ABC. Naturally, the largest the side having the largest length is opposite to the vertex having the largest angle, right. So, this vertex A has this largest angle 2 alpha, and therefore, the largest side must be this side BC, which is opposite to A, and since these are the lengths of the 3 sides, the largest one of them is x plus 1. So, it follows that this length must be x plus 1. Similarly, we know that the smallest side of any triangle is opposite to the smallest angle, which is alpha in this case. Therefore, this length should be x minus 1, and hence the remaining third side is of length x. If we now apply the sine law to this triangle, if we apply the sine law, then we know that x plus 1. So, sine law says that the length of a side divided by the sine of the angle opposite to that side is a constant, right. So, therefore, x plus 1 over sine 2 alpha is equal to x minus 1 over sine of alpha. And then if we since sine of 2a is 2 sine a cos a. So, using that identity, what we eventually get is that x plus 1 over x minus 1 is sine 2 alpha over sine alpha, which is equal to 2 times cos alpha. And then let us apply the cosine law to this angle alpha. So, from the cosine law, cos of alpha is equal to x square plus x plus 1 whole square minus x minus 1 whole square over 2 times x times x plus 1. But this is we have the same cos alpha here also. So, from this equation we know that cos alpha is equal to x plus 1 over 2 times x minus 1. So, that is from this particular equation, and therefore, this and this should be equal. So, let us simplify that on the next slide. In the previous slide we had so simplifying the expression from the previous slide, we have then taking the cross products, we get 2 times x minus 1 times x square plus. So, this is equal to 4x, and that is equal to 2x times x plus 1 whole square. X is a factor here, so we can write it as 2x into x minus 1 into x plus 4 equals 2x into x plus 1 whole square. Since x is the length of one of the sides of the triangle and it is a natural number, x is not equal to 0, and therefore, this implies that x minus 1 times x plus 4 is equal to x plus 1 whole square, which is equivalent to this equation, from where we see that x is equal to 5, and therefore, the sides of the triangle are 4, 5 and 6. So, this finishes the solution of the fourth problem. We now take the last problem of this lecture. So, in this problem it is stated that we have a n-sided regular polygon which is inscribed inside a circle of unit radius. The area of this inscribed regular polygon is denoted by In, and On is the area of the regular polygon which circumscribes the same circle. And then we are asked to show this relation between In and On. So, let us consider a circle in which we are inscribing this n-sided regular polygon. So, let these be the vertices of the n-sided regular polygon. So, there will be n vertices and all the n internal angles be equal. Let O be the center of this circle. So, let me denote this vertex by A1, A2, A3 till An, because there are n vertices. And it is given that the circle has unit radius. So, this is the radius of the circle, right. So, this is of unit length. This is also of unit length, and this angle, because it is a regular polygon, this angle will be equal to 2 pi over n. So, this angle is 2 pi over n, and then we will first find the area of this particular triangle here, OA1 A2, and because it is a regular polygon, there will be n such similar triangles in the polygon, and therefore, if we can find the area of this particular triangle, then we just need to multiply that by n, and that will give us the area of the entire polygon, right. So, we will take that approach. So, if I drop a perpendicular from the center of the circle O to this edge A1 A2 of the polygon, let this point be B. So, this is a perpendicular. Of course, because now this side is common, this angle and this angle are both 90 degrees, and this side are also equal. It is not very difficult to show that the triangle OA1B is congruent to the triangle OA2B. So, OA1B, this triangle, this right angle triangle, and OA2B are congruent because of the fact that we have a 90 degree here, their hypotenuse is of equal length, and they also have a common side, right. So, both of them are right angle triangles, and therefore, because they are congruent, it is easy to see that this point B is actually the midpoint of A1 A2. So, A1B is equal to A2B. And also, because they are congruent, what happens is that this angle and this angle also turn out to be equal to half of this entire angle. Therefore, each of these angles is pi over n, and then it is easy to find this length A1B, because if we see this right angle triangle OA1B, then A1B is equal to 1 times sine of pi by n, right, and that length is also equal to A to B, and therefore, the area of triangle OA1A2 is equal to half into base. So, the base is A1A2 and half of this base. So, half times base times height. So, height is this length of this perpendicular, which is OB, that is equal to, now half of A1A2 is nothing but A1B, because B is the midpoint of A1A2, and A1B is already computed to be equal to sine of pi by n. So, this times OB. So, OB again we can find out because we know this angle and this is 1, right. So, OB is clearly equal to cos of pi by n. So, this is the area of this triangle OA1 A2, and therefore, the area of the n-sided regular polygon is In equal to n times the area of triangle OA1 A2, which if we use this expression, then we get n times sin pi by n into cos pi by n. So, this is In. Now, let us also find On. So, On is nothing but it is said that we next have to consider the n-sided regular polygon which circumscribes the same circle, right. So, essentially we are interested in a polygon which circumscribes a circle of unit radius. So, we have a circle of unit radius and then we have a n-sided regular polygon like this, where these are the vertices. Okay. So, the vertices, let it be C1, C2, C3. This circle is the same as the circle in the previous diagram, right. So, the circle is same. In the first case, we considered the n-sided regular polygon which was inside the circle. Now, we are looking at the n-sided regular polygon which is circumscribing the circle. So, if we now connect the center of the circle to these two vertices of the regular polygon, and if you see this point here, so this point is actually the point of contact of the edge C1, C2 of the polygon with this circle, right. So, if we join this point with the center like this, then obviously because C1, C2 is a tangent. So, C1, C2 is a tangent at this point, let us mark it by D. So, what will happen is that this angle will be 90 degrees, right, and similarly this angle is also 90 degrees. This length OD is equal to 1 unit, because that is the radius of this circle. Next, our goal is to find the area of triangle OC1 C2, which we will be multiplying with n, and that will give us the area of the polygon, n-sided regular polygon circumscribing this circle. But this time we are given this length to be equal to 1 unit. In a very similar manner, it all again follows that both these angles will be equal to pi by n. because we again have a n-sided regular polygon, and because this is pi by n, this length C1d, which is also equal to C2d, will be equal to tangent of pi by n, right. And then it is very easy to calculate the area of triangle OC1 C2. So, this area will be equal to half times the base C1 C2, which will be equal to C1d, because d is the midpoint of C1 C2. So, half times the base is C1d, and C1d is tan pi by n times the height, and the height is 1 unit. So, the area is tan pi by n, and therefore, the area of the n-sided the regular polygon circumscribing the circle of unit radius is simply n times this area tan pi by n, which has been denoted as ON. So far we have I n equal to n sin pi by n times cos of pi by n, and ON equal to n times tan of pi by n. We were asked to prove this particular relation here. So, if we substitute the expressions, it is very easy now, because we just need to substitute the expressions of I n and O n on the right hand side and check if that is equal to the expression of I n on the left hand side. So, the right hand side is O n over 2 1 into 1 plus square root of 1 minus 2 I n over n whole square, which is equal to, so O n over 2 is n times tan pi by n over 2 times 1 plus square root of 1 minus, so 2 I n over n. So, 2 I n over n is equal to, so the division by n will just cancel this term, and the product with 2 will give us 2 sin pi by n into cos pi by n, which is equal to sin of 2 pi by n. So, here we have square of this. So, square of this is basically square of this, which is sin square of 2 pi over n, but 1 minus sin square theta is cos square theta. So, using that we get this to be equal to n tan pi by n over 2 into 1 plus cos of 2 pi by n, but we also know the identity that 1 plus cos theta is 2 cos square theta over 2. So, using this here we get cos square pi by n. So, this gets cancelled and we finally get n sin pi by n into cos pi by n, which is equal to the expression for I n. So, this finishes the proof of the solution to the last problem. In the next lecture, we will take some more problems like this. Thank you.